All right. Okay, so hello everyone. Welcome to this IQ seminar by Nicholas T. Bronn from the IBM Quantum team. So Nick, we're very happy to have you here with us today. Nick earned his Ph.D. in experimental condensed matter physics from the University of Illinois, and then he joined IBM Quantum as a postdoc in 2013. And since 2015, he's been a research staff member there. He's been responsible for developing and integrating quantum hardware and deploying quantum systems over the cloud. Nowadays, he focuses on enabling Qiskit on different hardware platforms, hardware-focused quantum applications, and education for the quantum community at large. So thank you again for being here with us today and talking about simulation of superconducting qubits using Qiskit, if I'm not mistaken. And the floor is yours.
Well, thank you very much for that introduction, and it's lovely to be here, albeit virtually. I'm very happy to talk about this new work from me, and I know my co-author John is in the audience, so we're very excited to present this new quantum simulation we're doing. So please feel free to ask questions. I think Maxim will be moderating, but I'm going to be covering a lot of material, and I'd be happy to answer your questions before we move on and get distracted by something else. So what I'd like to do is just kind of give an overview about the IBM Quantum Hub at Institut Quantique, an overview of Qiskit, which is how you'll access the IBM Quantum backends, a little bit about superconducting qubit control, which will be essential for understanding how we did the quantum simulation, but I'll give an overview of quantum simulation before we get into the control level of using Qiskit Pulse. The pulse level access was essential for realizing the ability to observe Majorana zero mode braiding, which is what we'll discuss at the end. Okay, so the IBM Quantum Hub at Institut Quantique is a new hub. I believe it opened up last year. It's the only IBM Quantum Hub in Canada, and by Quantum Hub I mean there are members of the hub as well. So I believe CMC Microsystems and University of Sherbrooke are the two members right now. It provides exclusive access to IBM Quantum's most advanced quantum processing systems. We have a community of world-class experts around the world. It's very international. We're very dedicated to education and quantum science, and we've been making a lot of educational materials together with Sherbrooke. And then certain kinds of IP and investments for Canadians. It's particular to why you want to have a hub inside your country, because the investment for the Canadian research can stay in Canada in this way, and the IP belongs completely within your organization by being a member of the IBM Q Hub at Institut Quantique. So that's just a little overview. Let's talk about Qiskit and superconducting qubits. So Qiskit is an open source framework for quantum computing that was developed by IBM. It's Apache 2.0 license, written in Python, and modular and extensible, and meant to interface with the IBM Quantum hardware, as well as any other kind of gate-based hardware. It's not really, it's intended to be open. It's intended to be used on any kind of gate-based quantum computing hardware, including currently working on ion traps and spins and some other labs. And basically what happens is we have these different elements of Qiskit. The bedrock of Qiskit is called Terra, and that's kind of the interface that allows you to build and run quantum circuits and interface with the actual quantum hardware. But then we have some other tools that are very useful, such as Ignis for characterizing and mitigating error. We're in the noisy quantum era, so errors are going to be with us, and we need to understand and mitigate them as much as possible. We have AIR, which is special purpose simulators, and which is useful for understanding noise and as well as understanding what kind of algorithms are going to be affected by that noise and how. And then finally, at the top level, we have Aqua, which is our framework code libraries for quantum algorithms, which is mainly geared towards the domain expert. If you're a domain expert in, say, chemistry, artificial intelligence, or finance, for example, those are the tools that will interface with you at a high level, so you don't need to know the gory details of what's going on at the interface of the hardware and software level. So we have a large community. We're hosted on PyPI, so you can download, and we're on GitHub. We have a Slack community, so we're very open. Anyone can download this and start playing with we have several open quantum systems for anyone, like 5 or 6 of those, and then we have like 13 or 14 premium devices, which are for, say, our hub members, clients. In particular, I'm going to talk about a part of Terra that is called Pulse, which offers you kind of, instead of the abstracted gate level of quantum computing, it will offer you a pulse level model, which is kind of where experimentalists like me have been, making our livelihoods. So what happens when you submit an algorithm to Qiskit? Well, this is kind of an overview of what happens now. Is you have an algorithm and say you're in Aqua and you want to calculate the ground state of a hydrogen molecule. One common algorithm for that is variational quantum eigensolver, but we have all kinds of other algorithms that are available as well, such as phase estimation and Grover's. What we're going to do then is we're going to compile this this circuit, which it's going to be compiled in some sort of quantum circuit, which is abstract in a way where you have a bunch of rotations around different axes of the block sphere, some controlled Z's or whatnot. But those circuits are not the ones that run on the actual quantum systems. Instead, they need to be transpiled into a quantum circuit that both respects the quantum architecture that we have on the back end and respects the native basis gate set. And this is something I'm going to keep coming back to because this was very important for this work. So basically, the transpiler does a bunch of things. It's going to look at the abstract circuit and start canceling redundant gates. And then once it's kind of simplified the abstract circuit, it's going to transpile it to the supported gates that can actually be run on the hardware and then figure out a mapping to the actual connectivity. There's a lot more, a lot more that can go on with the transpiler as well. It's a very interesting and active topic of research. Something we just made a contribution relevant to this as well. So this will get turned into a quantum object or a pulse quantum object or chasm quantum object, which will consist of a series of pulses or gates that will be able to be run. So for example, open pulse allows you to specify the pulse level access. And we can use these, say, for example, for error mitigation in the VQE algorithm. So this quantum object is kind of a large Python dictionary that gets bundled up and sent over the cloud to the IBM cloud, and then it gets converted to a queue where it goes to the queue where then it goes to an experimental backend and runs on a computer there, or it can go to other things such as chasm simulators or pulse simulators or one of the Qiskit air noise simulators, or it could go to some other quantum system as well. It doesn't have to be an IBM one. And essentially that will run a job, and that job will be returned as a result. That result will come back and say, if you have an algorithm where you're using VQE, where you're doing a lot of feedback, essentially this is like a classical quantum hybrid algorithm, then you're going to take those results and you're going to update the states you wish to prepare, and you will keep sending a job, so on and so forth. Now, we recently had a launch of a new software roadmap where we're trying to talk about how do we make our circuits run better, and how do we make them run faster. So there's a couple things I'm going to introduce here, and one of those things is dynamic circuits. So right now, you specify the circuit completely that you want to send this job, whether it's a pulse job or a circuit chasm for quantum assembly job. It gets sent to the cloud. It gets run on the back end, and it gets sent back to you. Now what happens is you can't branch, you can't do any conditional statements, you can't do an if-then, because the latency between the quantum computer and your own computer is too large. So what we envision is sending dynamic circuits to the back end, which will then run locally on some classical hardware that is next to the fridge, and that will be able to bridge the latency gap. And so not only will you be able to do branching statements in something we're calling real-term compute, where we can do operations within the coherence times of the circuits, of the qubits. We'll also have a near-time compute where we don't need that low of latency, but we have a low enough latency where you can run, say, a VQE algorithm where there's a lot of back and forth optimization and such, very close. And we forecasted that can be 100 times faster than the current run times of those algorithms. So right now we do have mid-circuit measurement and reset, but we don't have the ability to act on that, but that will be coming out later this year. I just wanted to show how this will be advancing. So let's take a look at superconducting qubits. So we really like superconducting qubits at IBM because it leverages all the skills and ability that we've developed over the years of CMOS, because it's built in much the same way, but instead of patterning semiconductors, we're patterning superconductors. So essentially we start out with say this is a 5-qubit device. All the parts you can see right now are a thin layer of niobium that sits on top of silicon. Now the silicon just kind of sits there and doesn't really contribute anything. The niobium is a superconductor, and it becomes superconducting at a temperature below 9 Kelvin, like many metals. Everything else is made out of aluminum, which is the smaller features, which becomes superconductor below 1 Kelvin. So this is a 5-qubit device. In fact, the first one we put on the cloud about almost 5 years ago now. And the qubits live inside these square pockets and pretty much look like these equal signs that have been rotated by 90 degrees. And so that equal sign actually represents the capacitor of the qubit. And if you look really, if you really zoom in, the aluminum features consist of something called a Josephson junction, which is a superconducting insulating superconductor interface. And that electrically behaves as a nonlinear inductor. So we kind of have like a nonlinear LC oscillator at this point. And the overlap of those junctions is about 100 by 100 nanometers squared with a 2 nanometer layer of aluminum oxide or so. So the other features that you have here are these big squiggly lines. These are superconducting microwave resonators. They're kind of coplanar waveguide resonators. It's kind of like a coax that's been flattened out to 2D. These are used for a number of things. For example, to couple the qubits to the outside environment to assist in readouts, but they also persist. They also help with protection because their frequencies are detuned from that of the qubit. And they're also used to couple the qubits together. So without qubits interacting with each other, you don't get the benefits of entanglement that gives us the promise of quantum computing. So what's kind of the difference in the energy scales of these things? Well, the transmission line resonators act as LC oscillators or harmonic oscillators, depending on which classes you took in undergrad. And you'll know for either of those systems that you have a parabolic energy profile, and that gives you energy level spacings that are equal to each other. Now, the problem with that is we can't use this as a qubit. Normally, you'd like to say, I can use the ground state as a 0, and I can use the first excited state as a 1. But the problem here is if you try to drive transitions between the 0 and 1, you'll end up exciting higher order transitions as well. There are ways you can kind of get around that using other kinds of states, but in general, it's not very good for us. Instead, we use this thing called the transmon superconducting qubit, which has this nonlinear inductance, which gives us a more of a cosinusoidal profile, which means the energy level spacing between 0, the ground state, and 1, the first excited state, is going to be different between that and the 1 to 2 state. And because these energy levels are different, we can address the 0 and 1 level separately, and we can essentially isolate our transmon, which is multi-level, into a qubit, which is a 2-level system. And so then one thing I should add here is that the energy level spacing here is about 5 gigahertz in frequency. And if you multiply that by Planck's constant divided by Boltzmann's constant, you'll see that that comes to a temperature of 240 millikelvin. Now, 240 millikelvin is substantially colder than the critical temperatures of the superconductors we're using to make them. And because we want to have a well-defined energy state, we need to be at a fraction of this temperature when we're operating. So we're actually the reason why we need to be so low in temperature is because we need to be a very small fraction of this 240 millikelvin, the energy spacing of our qubits. So that's why we're operating at 10 millikelvin, in case you've ever wondered. Okay, so how do we control these qubits? First, I'm going to return to the kind of mathematical definition of the Bloch sphere, which you've probably seen. The Bloch sphere represents any superposition of 0 and 1 on the surface of a sphere, where you can have complex superpositions. So basically, matrix-wise, we write these in Dirac notation where the state 0 stands for the column vector 1, 0, and the state 1 stands for the column vector 0, 1. And then we can operate on those. All our operations are unitary matrices. So there's a special class of matrices called the polymatrices, which define the axes of measurement. And as you can see here, we actually use the Z basis for measurement in superconducting qubits, where the 0 state has an eigenvalue 1, and the 1 state has the eigenvalue -1. But these polymatrices also do something else special, is they generate the rotations around the Bloch sphere. So if you remember from your quantum mechanics class, you can exponentiate this this vector of polymatrices with a normal vector that you would like to rotate around your axis in the Bloch sphere. And you can essentially, because the polymatrices have a nice algebra, you can write down a pretty simple formula for what the unitary of a rotation of an angle theta about that axis would be. And so, for example, we can rotate around the x-axis by just pulling out the x polymatrix here, and we get this simple 2x2 SU2 rotation, which will take us around the Bloch sphere around the x-axis. So what does this mean in the lab? Well, physically, what we're doing is we're hitting the qubits with microwave pulses. So these are microwave pulses around the carrier frequency around 5 gigahertz, the transition frequency of the qubits, and they're typically shaped in some sort of Gaussian manner. It's actually not quite Gaussian. I'll kind of show that later, but it can be pretty much understood as a Gaussian. And what that does is that will rotate you around any axis in the XY plane of the Bloch sphere. So, for example, the only difference between a rotation around the x-axis and rotation around the y-axis is that phase has been shifted 90 degrees, and that will generate the different angles of rotation. What about z rotations? Well, we can combine x and y rotations together to get z rotations, but it turns out we can actually compile the z rotations away in software, because z rotations are just going to change the phase of the subsequent gates. We can kind of compile that in hardware and get the z rotations for free. So we just shift the phases of the subsequent pulses, and we can show using randomized benchmarking that you get an average lower error rate. So this is actually how things are done on the back end. How about 2 qubits? Well, a lot of people think about like what makes a universal quantum computer. Well, it's a very similar concept to what makes a universal classical computer, and that's that you need to have a certain ability to do all the Boolean operations you need to, and likewise for you need to be able to do all the SU4 operations you need to. So for a classical computer, what's this look like? Well, it looks like you can use either a not and or a not or gate. Either one of these will give you a universal classical computer, and these are just the truth tables for these that make up the Boolean logic. So 0 and 0 is 0, and if you not that, that's 1. So that's what a NAND will do. 1 and 1 is 1, so not that is 0. And then similarly for NOR, you can look at the truth table for that. Now, actually, one of the interesting things about this is you can see there's 2 inputs and 1 output, which means this is not a reversible process, which means this is not achieved with unitary operations. So this does not work for quantum mechanics. So we have other 2-qubit operations we can do. So pretty much for quantum computers, you need a set of single qubit rotations. You don't even need all of them, but I already showed you can pretty much easily get all of them. And any 2-qubit operation, and this is where things start to differ a lot, even for the superconducting qubit architecture. So there's probably the best example from your quantum computing class is the controlled knot. What this does is it will flip the second qubit or the target qubit dependent on the state of the control qubit or first qubit. So in the input, if you have 0, 0, your control qubit's 0. It does nothing to the target qubit. So 0, 0 goes to 0, 0, and likewise 0, 1 goes to 0, 1. But however, when the control's in 1, such as 1, 0, 1, 1, you flip the target qubit. So 1, 0 goes to 1, 1, 1, 1 goes to 1, 0. And you can see here there's 2 inputs and 2 outputs. And then you can also see that if you were to put your control qubit in a superposition of 0 and 1, so you'd start in a, say, 0, 0 plus 1, 0 state, then you apply to C naught, you would get a 0, 0 plus 1, 1 state, which is a maximally entangled Bell state. So this shows that in this way you can show that you can achieve any kind of quantum operation. But it's not the only one you can do. You can also use a controlled phase gate. What the controlled phase gate does is it puts a minus sign or 180-degree phase on the state in which both qubits are in the 1 state. And there's also more complicated ones, such as the I swap, where it swaps the order of the qubits, and it gives you an I, the imaginary number, square root of -1 in front of it if something actually happened. And so depending on the actual physics of your devices, you're going to choose one of these as your native 2-qubit gate. Now, how's this actually done? Or no, I'm going to go through some math a little bit more. So how's this actually done? Mathematically, we use something called a cross-resonance operation, which is a physical operation from which we extract something called a ZX operation. So the ZX operation can be just understood how we did the rotations before. You take the Z and X Pauli matrices and tensor product them together, and then you exponentiate them using that formula in just the same way. And what you'll see here is in this unitary that I've generated, the 4x4, the upper left block in which the control qubit is in the 0 state, the subspace in which the control qubit is in the 0 state, corresponds to a positive rotation around the x-axis in the block sphere. However, if you look at the lower right, the subspace in which the control qubit is in the 1 state, you'll see it's the opposite rotation around the x-axis. So in this way, you get a rotation of the target qubit that depends on the state of the control qubit. So let's look at this a little more visually. And as physicists, we like to think about things in a basis, and then we can add and subtract them and form superpositions out of them. So right now, let's just consider the purple vector, where the control qubit starts in the 0. And we'll say the target qubit starts in the 0. For superconducting qubits, we always start in the 0 state because it's the ground state. So if I was in the situation where I'm just looking at the purple now, and I apply a cross-resonance operation to the control qubit, my target qubit would start rotating to the right here, which is why it's kind of off the 0 to the right. However, if we consider the situation now, I've now prepared my control qubit in the 1 state by applying a pi pulse. So we're just looking at the blue vector, and my target's in the blue, and it's starting at the 0. And I apply a cross-resonance, then my target qubit is rotating to the left. So these these two qubits are going in opposite directions depending on the state of the control qubit. So what happens is if I prepare my control qubit in a superposition of 0 plus 1, then what happens when I apply the cross resonance is my target qubit is effectively going both directions, which is how they're becoming entangled, which is why I can't really draw that on this graph. So kind of like mathematically, that's what happened. Now, physically, things get a little bit more complicated. The reason we like the cross-resonance gate is because it's an all-microwave entangling gate, and that allows us to have fixed frequency transmons. By fixed frequency transmons, I mean they have no loop in them in which you can tune the frequency of them. It's a single Josephson junction, and due to the natural spread of forming this glassy Josephson junction, which changes the critical current, which in turn changes the frequency of the qubits, we get a natural variation in frequency between those, which is necessary for the cross-resonance gate. But we don't have any extra control knobs, and that's why we really like it. So what happens is, if we just had two qubits lying around, they would have, and they're not interacting with each other, they would have this energy level diagram where the control here is a little bit less in frequency than the target. And then I'm going to specify this capital delta as the detuning between those two frequencies. So you can see the frequency omega-1 of the control qubit, the first one, and the frequency omega-2 of the target qubit. What I'm going to do now is I've actually put a bus there, and this bus is the microwave transmission line resonator we were talking about. And what that does is introduce an effective coupling J, which is going to hybridize the qubit slightly. And I think this should be plus or minus J squared over delta. I think that 2 needs to go away. But it's going to shift the energy levels very slightly. So the control remains mostly like the control qubit. The target qubit remains mostly like the target qubit. And this is something we call the dispersive regime, where things become a little like the other one, but not entirely. And if you look at what happens to the wave functions, you'll see that the excited state of the control qubit is mostly like the excited state of the control qubit, but with a little slightly excited state of the target qubit. And that I know that's slight because this J coupling is about, say, 3 megahertz, and this delta is about, say, 50 megahertz or something. So it's a very small amount of the control that's becoming like a target, and a very small amount of the target that's becoming like the control. So when I want to operate the cross resonance, or if I want to operate single qubit gates, I'll apply pulses at the control frequency to control the frequency of the control qubit omega-1 to do single qubit rotations, and likewise for single qubit rotations of the target qubit, I'll do rotations at omega-2. Now, if I want to do cross resonance, though, I'm going to drive the control qubit, but at the frequency of the target qubit. And so then what happens is you're driving the hybridized part of the control qubit, which is this other part of the target qubit. And because you get the sign difference, that's what gives you the effective ZX interaction that we're using. And so this pretty much corresponds to whether the controls in the 0 or 1 state, we're driving Rabi oscillations between one of those levels, either between 0, 0 and 0, 1, or 1, 0 and 1, 1. And that's how the opposite sign accumulates. So that's the physics of how we do these two qubit operations, and we'll see a little bit more of that later. But first, let's take an overview of quantum simulation. If there's no questions, maybe I should take a little break for questions.
I don't see any question yet, but
all right. Well, I'll just keep on going then. All right, so let's talk about quantum simulation. So I think
actually there is a question. So
yeah, please go ahead.
So Eric, maybe you can ask out. Eric, if you want to ask your question. I don't know if your microphone is not working.
I don't. Maybe he's on mute.
Yeah, it doesn't look to be on mute, but we don't hear him. So.
Well, you can try the chat, I guess, if
yeah,
we can come back to it.
Thanks.
But yeah, I'm going to start with the overview of quantum simulation. So one of the big impetuses behind quantum computing was Richard Feynman in 1981, noticing that nature isn't classical. He was having a very hard time simulating quantum mechanical phenomenon using classical computers. So if you really want to understand quantum mechanical phenomenon, you'd really like to put that on a computer that obeyed the same physical laws. And so this was kind of the first idea of quantum computing. And probably one of its most promising uses is the simulation of other quantum systems. So basically, what's the idea behind that? Well, I have a quantum system, and I know it evolves from some state phi 0 to some state phi t, and that evolution is going to happen under a unitary U. Well, I can achieve the same thing if I can map that to another quantum system. So I can map my phi to psi, and I can do my evolution with this u prime instead. And I can do my preparation so that I get the same initial state in that map system. I do a different evolution that but corresponds to that, and then I can measure it, map it back to something where I can get the answer. And the only difference is the quantum system evolves with this Hamiltonian H-cis, and the simulation will evolve with this Hamiltonian H-sim. And so the basic idea of digital quantum simulation is how do I transfer these systems from one to the other? So this quantum simulator here, in this case, will be our quantum computer. But this doesn't have to be a quantum computer. It could be a quantum simulator such as cold neutral atoms, for example. An example from chemistry, which we work a lot on, is mapping molecular orbitals, which obey fermionic statistics, to the spin Hamiltonian that the quantum computer obeys. And one way you can map these fermionic Hamiltonians is by taking the operators and doing something called a Jordan-Wigner decomposition. This is not the only way you can do that. There's several different ways. Bravyi-Kitaev, BK superfast parity come to mind. But it essentially involves taking the operators that describe fermions and mapping them to a system that describes spins or qubits. So instead of a fermionic Hamiltonian you might have from chemistry, you get a string of we call a superposition of polystrings, where these polystrings consist of they're strings of the Pauli matrices used for measurement or for evolution. So basically, for running digital circuits, I can build everything I need to out of say a prototypical ZZ. I actually went back to Mike and Ike's quantum computation and quantum information for this, and their example wasn't as good, but I found another review paper that kind of describes this better. So we'll go through this. So if I want to do a ZZ interaction between two qubits, I can do a C naught, a rotation of Z on one and another C naught. And I can turn that into other things by applying these identities. So if I want to get, say, a single qubit X gate, I can sandwich a Z with two H's. If I want to apply a single qubit Y gate, I can sandwich a Z with the square root of X and the square root of X dagger. So then I can get, say, other interactions such as a XY interaction, and sometimes we use little Indian notation, so the qubit order is reversed. So this would be a like YX interaction. So I just take the I just sandwich the terms that I wanted from the ZZ, and I can get these new kinds of interactions. And this is something that you can extend in general. So essentially anything you can write as a string of polys, this gives you a formula for how to, this kind of a first step for a unitary operation of how to simulate it. Of course, the next thing is you need to account for the fact that these terms will typically not commute with each other. So you need to do some special things, such as breaking that down and that's often called the Suzuki-Trotter decomposition. And these are, the kinds of steps that we use to do this work. So we are going to apply this to a Majorana zero mode. So it's kind of a toy Hamiltonian that we can go through the Jordan-Wigner decomposition and Suzuki-Trotter decomposition in order to map this to a quantum computer. And that's what I'm going to be talking about for the, and then Qiskit Pulse about how we did that more efficiently for the rest of the time. So Majorana zero modes are these special particles that were hypothesized to exist in the 1930s by Ettore Majorana, who famously disappeared after proposing them. They're fermionic particles that are hypothesized to be their own antiparticle. They were thinking for a while it had to do with neutrinos, but I don't think they think that anymore. They're also predicted to obey non-abelian statistics, which is very interesting because they're composite particles. The phases will pick up in different ways that are not quite like fermionic or bosonic. And then physically, there's a number of systems in which these have been thought to arise, but one of the more recent ones is thinking of them as non-local modes with even and odd parities that appear at the end of a nanowire. This nanowire needs to have a large spin orbit coupling and needs to be proximatized by an S-wave superconductor in order to approximate the Hamiltonian of a spinless P-wave superconductor. So what happens is people found if you have a spinless P-wave superconductor, you can show the existence of Majorana zero modes. However, that doesn't really exist in nature, so you try and approximate it by using S-wave superconductors and spin orbit coupling nanowires. And so then your model system is kind of based upon this this nanowire where you have a chemical potential mu, you have a hopping term T, and then you have a superconducting gap delta. And if you tune these the right way, you can form Majorana zero modes at either ends of those, and those are the composite fermion. So let's look at the Hamiltonian for this. So in this basic braiding demo, we're considering 3 nanowires forming a trijunction, and these Majoranas on each one are coupled to each other by an amount alpha. So that first term in the Hamiltonian is alpha, and then the nanowires are coupled to each other by these termed J's. J's. So these are the inter wire couplings, and those are the things that we're going to manipulate. So if we start in the initial position where we have J01 is equal to J max, then we have effectively fused the top 2 nanowires together into a horizontal line, and the other Majoranas are gapped out, so we don't have to consider them. And we can do a braiding process between these 2 Majoranas starting from this coupling. So from going through this time evolution where we take J01 and we reduce it from J max to 0 and J12 from 0 to J max, we can officially transfer this Majorana on the left to the Majorana on the bottom. So basically we have 2 Majoranas but 3 modes, and these modes are the ones that we're changing the strength of in order to do the braiding. So now that J12 is equal to J max, we're in this configuration. I can do the next step, which is to take that J12 and drop it to 0 and bring J20 up. And what that will do is move the Majorana from the right to the left. And then as I go back, I can now get back to the original position where I'm at J01 is equal to J max, but you'll notice that the Majoranas are not back to their original positions. They're opposite of each other. So what happens now is we need to go through this one more time to get back to the original position. So we'll take J01 to 0 again, J12 to J max, and so we just keep moving the Majoranas around like that. And we're back to the original position. And so that's six steps in order to do this braiding, and that's how we perform the quantum simulation. So we have the ground state, or sorry, the parity of the wave function. We'll start in the psi plus state or minus state. We could do either way. And what happens is there's still a degeneracy, or there's still coupling, so the degeneracy is broken into the excited plus or minus the ground state. And then what happens is, as we do this braiding, we want to get to the other parity, which is energetically different. But if you had a perfect 0 modes, they would be the same energy, but it would be the opposite side. Okay, so basically the formula for how you want to do this is you're given your trijunction Hamiltonian. You go through and apply some transformation. In this case, we applied the Jordan-Wigner transformation. And you can see how the Majorana is mapped here, where this A is corresponding to X or Y in the picture before. And then the corresponding to the X or Y Pauli matrix corresponding to which qubit we're mapping it to. So then we arrive at a spin Hamiltonian, which is something that we can formulaically map to a quantum computer, which is nice. And then we need to do a Suzuki-Trotter decomposition, which in this case we applied the steps in one way, where the operators go in one way, and then the next step with the operators in the reverse way, in effect getting a second order decomposition. So I'll refer to things as braiding steps and Trotter steps, essentially, because each one of these is a separate unit of the evolution of the Hamiltonian. So what happens when you map this onto a quantum computer? So this is a 3-qubit Hamiltonian, and we can essentially take each one of the terms of the Hamiltonian and put it right on the, formulaically put it right on the quantum computer using, it's still in the abstract gate method, but using those techniques we showed earlier. However, we're going to be using this IBM Q Athens device, which is a 5-qubit device where all the qubits are arranged in a line. And when we actually map it to a physical system, we start to notice some problems, some things where things might go wrong. The first thing is that I didn't really tell you the error rates of all the quantum operations, but the single qubit rotations are pretty light to the tune of about 0.1% error. But the C naughts, whenever you're going to count a C naught, you're going to get about 1% error. And so that's those are going to accumulate if you're not careful. So let's look at some other gates. Well, we've got these controlled Z's here. These also have C naughts in them, so I'm going to have 1% error plus a couple single qubit errors. And then if I look at this other C naught over here, well, that's going to require a swap because these qubits are arranged in a line, and I can't do a quantum. I can't directly do a quantum operation between Q0 and Q2, so I got to do the swap operation. So this is going to be 4 C naughts. That's very expensive. The other thing to notice is that these terms that we're actually rotating by, so for this YX interaction, for example, it's not very large. It's typically on the order of pi/10 to pi. Each one of these C naughts consists of a ZX operation to an angle of pi/2. So essentially what's happening is for each one of these like kind of digital formulaic operations, I'm doing a pi's worth of entanglement, but I only need pi over 10 to pi over 3. And this is where John and I started talking, and I'm like, well, you know, we can get around this if we started using Qiskit Pulse. So let me give you a little overview of Qiskit Pulse. So what motivates Qiskit Pulse? Well, the ability to program quantum computers over the cloud, just like you were in the lab, like I've spent the last, you know, from 2013 to 2019, 2020 or so in the lab, you know, making the pulses myself. This allows you to do it from anywhere, you know, over the cloud. And there's a lot of reasons why you'd like to do that. Some of the examples are optimal control. So for example, you can form extremely short single qubit gates using optimal control of piecewise constant functions that don't excite your qubit to the higher state, and they were able to get down to about 4 nanoseconds, which is substantially less than the like 20 or 30 nanoseconds that we use for single qubit operations now. We can also use error mitigation. Here's a technique called Richardson's extrapolation that what essentially happens is you perform your same circuit, but you recalibrate the pulses to make them longer in order to induce a controlled amount of incoherent error in the system in a controlled way so that you can try and scale back to the case where there was 0 error. And we showed that that actually works. And there's other kinds of quantum error mitigation, such as dynamical decoupling, where you can like refocus the coherent interactions or even noise, low frequency noise in certain ways that that gets you a higher fidelity process. And so just kind of an overview of how this works. We gave you certain channels in which you can play pulses out on or acquire on, and these essentially consist of 4 of these, and I just want to introduce them so that they'll make sense later. We have the drive channel, which is typically the single qubit control, the on-resonant control. We have the control channel, which is typically the off-resonant control channel, which is used for cross-resonance. We have the measurement channel, which happens at a completely different frequency, typically around 7 gigahertz for our systems. And then the acquire channel, which is going to digitize the result of that measurement. And so they're specified by these D, U, M, and A terms in the plots I'll show. And the kinds of instructions I can do on them is I can play a pulse. So I'm sending a microwave pulse down the channel. I can delay, I can add a delay, say, between pulses or something else. I can do a frame change, which is equivalent to that Z rotation done in software, which changes essentially the running phase of the circuit to induce a Z rotation. And I can acquire, which that only happens on the acquire channel. So basically what happens is if you have this gate level model of, say, forming a Bell state by doing a Hadamard to Q0 and then a C naught to give you the 0, 0 plus 1, 1 state, well, what's actually happening at a pulse level and what's happening down under the hood is where, you know, experimentalists like me live. And I can tell you that you see most of these things, most of the pulses are happening on the drive channel of qubit 0 and the drive channel of qubit 1, but we also have these big yellow pulses, which are the cross resonance pulses, which are happening on the control channel of qubit 1, which means it's actually going the opposite way because it's going to be operating at the frequency of Q0. And then we have these measurement and acquire pulses, but we're not really going to focus on those right now. What we do want to notice about these pulses is there's like details to them that make big differences to how we operate the quantum computers. So, for example, here are the frame changes I told you. These are the Z rotations done in software. So it just changes the phases of the subsequent pulses, for example. We also have these techniques called drags. So I said these pulses weren't exactly a Gaussian shape, but they are actually Gaussian with the addition of a derivative of a Gaussian on the quadrature channel. So you just add up that 90 degrees out of phase and you get this, well, nominally to reduce leakage, but it actually just kind of gets rid of other kinds of errors such as line dispersion and effects from higher order or effects from the higher order levels of the transmons. So that's kind of the typical default one. We also have an echo pulse. So what this does is there's extra terms in the cross resonance Hamiltonian I did not tell you about. This will get rid of them nominally if we had a qubit. But we have actually a transmon, so we have even more terms come along for the ride, which we'd like to suppress, such as IY and ZZ. And these rotary echoes are our new technique that we just recently published on last summer that tell you how you can get rid of, all the, how best can you get rid of all the undesired terms of your cross-resonance Hamiltonian to leave you only the desired ZX from which you can build C naughts out of. So these are all the kind of tricks under the hood that I know. And so what we talked about as well, we are using too much entanglement for what we need to do. Especially, you're going to be taking this time evolution, which is going to involve all these Trotter steps. You're typically not doing large angle rotations when you're doing quantum simulation. So why don't we scale that circuit down into something that respects the hardware a little bit better? And so what we did was we formed this pulse circuit now, where each one of these rotations is done by, or each one of these gates is done by a pulse, and you can kind of go back and forth. But in particular, we have these A gates, or atomic or analog gates, which essentially consist of just the bare echoed cross resonance. So you can think of this as isolating just the entangling part of your 2-qubit operation. And then you can understand the interactions by adding a pi/2 rotation to the beginning and end of that on qubit 1, and that will realize you a YX rotation, which consists of the kind of inherent ZX rotation with a couple single qubit rotations on top of that. So that whole schedule now is forming this YX pulse. So we've actually even gone forward and simplified the single qubit gates a little bit more. And that YX interaction is exactly the same YX interaction that you get from this digital simulation, consisting of 2 C0s and a Y rotation. So one of the things we noticed is that, well, by scaling the lengths of these pulses, so we know because of the way the 2-qubit gates are tuned up, that they're pretty much at the shortest length that can be made without getting up to an amplitude that will cause leakage to higher order levels of the system, which is always a problem in cross resonance. And I can invite you to look at all the research we publish on the cross resonance gate. Everything gets very, very complicated very, very quickly. So what we can do instead is shorten these pulses and get just the area under the curve that we desire for the ZX interaction. We can lower the amplitude if we need to, if we need a smaller angle, but we never want to increase it. We can just go back and forth in this width, and that's exactly what we did to realize these analog YX rotations. And if we do quantum process tomography, we notice that we can get an advantage, especially when we're going to those smaller angles, because as we're going to smaller angles, we're doing less and less entangling. So the smaller angles correspond to the process fidelity, process tomography that occurred. Yeah, the fidelity you get from the analog type pulses is in this orange right here, whereas in the blue you get the process tomography of the digital kind of formulated pulses, which is not going to change in angle because an RY at any angle is going to be just as expensive. It doesn't matter what the angle is, you still have 2 C0s coming. So as expected, we got a pretty much flat variation. Of course, there's always drifts in the systems because these were run over a few days. But basically, it's a pretty flat line, and it's always lower than the analog line, which kind of goes linearly down, which we found kind of agreed with our error model. So this, in a way, if we subtracted these two curves, we can see we get a relative improvement of a lot if we switch to these analog type pulses. And one of the special things about them is that we don't even need to do recalibration of these. We can just scale them analytically to make the area under the curve match the area of entanglement that we desire. So no further calibration. It makes it very easy to run in the current cloud-based systems. The other thing you can notice.
Can I ask a question just on previous? Maybe you mentioned it. I'm just wondering. So, like in the first circuit at the top, you have this C0 between all pairs of qubits. And then when you do the pulse one, you're losing this. There is no interaction between the first qubit and the last qubit.
That's right. So that's a great. That's a great notice. So as it turns out, for these three that we can, because we can like transpile the C0s that need to happen. And the C0s also have a preferred direction. So we were able to do this so that there was no need for the 0 and the 2 to be directly entangled with each other. It was all done via Q1. And essentially, like I would say, hand transpiled by John down into these atomic echoed cross resonance gates.
Okay, thanks.
No problem. Yeah, that's a great notice. Anything else? Okay, well, I'll continue on. So one of the ways you can really see what happens is if you look at, say, one of the steps. So if we look at a single Trotter step in one of the braiding steps, and this is the first one, different from the 0th one, so it's actually the second one. You can look at the pulse schedules that are generated by what each circuit would do. And I can see right now where I have the scaled ones. I'm doing a lot less of the yellow. That's the cross resonance pulses, and that's where most of my error is coming from. So not only is the schedule a lot shorter, in fact, it's only 60% of the length of the the digital schedule, but the area under the curve is also extremely low compared to the right. So I'm still using less entanglement. So if there's more error that's coming not just from the decoherence that's happening during the pulses, but also additional error that's happening because of other effects occurring during the cross resonance pulse, that is also being somewhat mitigated by this scaling. And so that's why I like this plot, is because you can really see it, side to side. And when we do that, we can actually you can bring us to the braiding, but first we'd like to analyze what happens when you do one braid step, which is just a sixth of the entire full braiding steps. Remember, there's 6 steps to the braiding. Then we can compare what happens when we use the digital and scaled circuits. And one of the reasons we did this is because if you try and do the full thing digitally, you get to just noise. And so we run this by preparing the preparing the state in the psi plus state. And we're actually mapping back to the psi plus state. We map back to the original state because you can do that. You can choose whatever basis you want. So psi plus is the successful case and psi minus is the unsuccessful case. Now there's some amount of adiabaticity. So even in the noiseless circuits, you're going to have errors caused by the adiabaticity, and your errors in the actual experiments can be adiabaticity plus leakage plus decoherence. So there can be other things happening. So we kind of just throw those states away because we expect there to be higher energy level states, and we're just focused on the proportion or the probability of measuring the psi plus or psi minus states. So what we see is in the scaled case, if we run this on a simulator, the Qiskit Chasm simulator, we see in the noiseless case we get the best fidelity, in that you have the highest contrast between psi plus and psi minus. But we do very well even on the real device. In fact, we still do even better than the noiseless case of the basis gates. And if we look to see the basis, the basis being run on the actual IBM Q Athens suffers from the highest amount of error at that level. And then, so when we actually did the braiding and we went to the full simulated system on the actual IBM Q Athens backend, we could model that error. So this is going to show you the contrast between the P plus and P minus. And you can see that this separation away from 0 indicates that we've successfully braided the MZMs together. So this is for a 6 tau corresponding to 6 of the braiding time steps. What we did here was we wanted to mimic the effect of the full C knots on the effect of the simulation. So we just actually added time delays on either side of the entanglers. And we can specify that at the bottom in terms of nanoseconds, or on the top in terms of a fraction of a C naught time. And what we can see is we're essentially artificially adding incoherent error to the system. And we see after a delay of a little over 100 nanoseconds, you've completely lost distinguishability between braiding and not braiding. So we're quite happy with the performance that this shows, that this has brought us back to the level where we tried to do this digitally on the IBM Q Athens backend, and we're unsuccessful. We weren't able to do it successfully, and this demonstrates why that was not successful. So this is great, and we've thought about this already, and I just want to do my conclusions and kind of get any questions we have time for. Is that we've learned a lot from this. We know that noisy quantum computers were going to be with us for a while. So there's a lot of smart pulse things that you can do in order to implement your algorithms more efficiently, by knowing exactly, being a little bit more familiar with what's going on in the back end. But then we can also bring that up a level. And so, for example, this system of scaling the pulses has now been added to the Qiskit, well, at least the development branch of Qiskit, from this pull request from one of our other co-authors, where we can essentially let the transpiler be aware that there is the ability to do these use these echoed cross resonance to break down interactions in a smarter way. So this kind of goes hand in hand with having pulse level access and efficiently transpiling the circuits that you want to do into something that will run better. There's a lot of other kinds of systems that we're adding. So one thing we just started touting was our ability to do mid-circuit measurement and reset. For example, in these noisy systems, this allows you to do iterative phase estimation using a smaller set of qubit resources. If you have the ability to do mid-circuit measurement, then you can implement algorithms more efficiently. than you would be able to if you were doing the straight phase estimation algorithm using a larger register of qubits. So these are the kinds of things. Dynamic quantum circuits are just going to open up a larger ability to do different kinds of quantum circuits that we probably haven't even thought of yet. So there's kind of a wealth of development going on that provides the ability to, squeeze the most kind of performance out of your quantum computer. And as someone who works on kind of low level, pulse level, transpilation level, I think this is a very exciting time for me and for everyone who gets to use this kind of stuff. So some of these techniques we've already used to improve quantum volume. And just like to say that by bringing all these resources to bear, we're enabling our users to improve algorithms and be able to do more with the quantum systems of today and tomorrow. So thank you very much for your time, and I would appreciate any questions.
Thank you, Nick. It was a very nice, a very nice talk. I really like that you describe the physical problem you were trying to solve, and you go down to the pulse. It's the full stack of the problems. It's a very nice presentation. I would just like to open open a welcome to an invitation to the participant of this talk, that just say that because you're at the University of Sherbrooke and the Institut Quantique, you have access to this machine. You have access to Qiskit. Everything here that Nick has presented, if you want to do it, actually you can do. So I just want to open the invitation, and please reach out to us at Espace IBMQ for that. So maybe we can take a couple of questions. We have still a couple of minutes left. So I know that Eric had a question earlier. I don't know if you managed to make your microphone work.
Are you able to hear me now?
Yes. Yeah, we can hear you, Eric.
Yeah, sorry. For whatever reason, Teams has this problem that when I'm on mute for a while, it just forgets my microphone. Thank you. This was an amazing talk. And I read your paper last night, and listening to this talk today, I feel like I didn't read that paper. So this was just an amazing talk. So thank you.
Thank you very much.
Yeah, my reading comprehension skills could be improved. So not super specific to this, but I was kind of just wondering how much one is able to mix and match open pulse and the transpilation on what you're doing here with kind of a more gate level type thing. So for instance, if one wanted to specify a new C0 type gate like what you showed, would you be able to do that and then use the rest of the different Qiskit framework? Or if you're going at the pulse level, do you have to fully specify the entire circuit all at the pulse level?
Yeah, that's a great question, Eric. And this is also something that is somewhat changing. If you've seen our OpenQASM 3 specification, which I think you have, then you'll know that pulse is going to be subsumed by OpenQASM 3. I don't know if it's going to make any effect in Qiskit, but there's already ways to kind of go between the gate level. If you go back, if we go back to the not the original pulse paper, but kind of I call it the second pulse paper, this guy. This kind of shows you how you can use pulse to build your own C0 gate. So that's what the point of this paper was, is they calibrated their own C0 gate out of just using pulse, and then they added it as their own native gate, and they were able to benchmark that. So I think they did QPT as well. But you can do randomized benchmarking as well. In fact, we have a calibrated S gate, a controlled S gate, which was done by a couple of our team, where they invented a new kind of randomized benchmarking, like dihedral benchmarking, in order to benchmark the new kinds of gates that you come up with using pulse. So actually that brings up a very interesting question, because I was thinking about this idea is this echoed cross resonance. There's actually a little bit more complicated than that, because there's always a preferred direction. It just always works better in some direction for some reason, probably because of the way the frequencies and anharmonicities and spectators are aligned. So you always build your C0 out of either the forward or the reverse echoed cross resonance. So my initial idea was to modify the basis gates. You can change your own basis gates in Qiskit and take out the C0 and put in forward echoed cross resonance and reverse echoed cross resonance, and then inform the transpiler that those were the native basis gate sets. So in that way, you would not need to be building these things at a pulse level, but your transpiler would be able to figure out how to break whatever you wanted that down into your native basis gate set. So, and actually instead, which is a little bit smarter, is this template optimization thing, which Daniel did, and quickly submitted it for a pull request. So this was only a few days ago, and what this does is it's a newer process called template matching, which was developed by our algorithms team in Zurich. And what it will do is not just break down the interaction you want to do into a number of pulses that you can do on the back end, but it will also combine pulses where it sees in the right way so that it can maybe do higher level optimizations. So I haven't completely read or understood the paper, but that's what I know. And the other advantage of this is this makes it so that the user doesn't have to be aware of the backend as much. So it doesn't expose the user to the backend details. So it's kind of a better method going forward as well. It'll be easier to use, say, if you're just trying to do a quantum simulation and you want to set up your algorithm to do exactly what we did. So, thanks for the question, Eric.
Yeah, you're welcome. And you mentioned a paper. Is there a paper that corresponds to that pull request?
No, there's no paper there. Sorry, there's a paper on template optimization, Stefan Warner.
Okay.
So that is what the template optimizer is based on. And this is essentially a template optimization Daniel wrote that uses that template matching algorithm, but uses it for specifically this breaking down the gates into the native basis gates for quantum simulation.
Thank you very much.
No problem.
Maybe I can ask a very, very quick question. I didn't play a lot with OpenPulse yet. I was just wondering at the beginning, you mentioned a pulse simulator. Is there a pulse simulator in Qiskit right now?
Yes, there is a pulse simulator. And in fact, John and I actually worked out all our kind of kinks on the pulse simulator beforehand. However, it is not very fast. And when you if you want to run, like say one of the things we were doing was Hamiltonian tomography, which we used to extract the cross resonance terms, or it's used to extract the terms of any block diagonal drive Hamiltonian. And what we found is we could run that, but it would take hours on the it would take hours on a pulse simulator, whereas if we ran it on the actual devices, which I should also say John had access to through our research access awards for the IBM Quantum experience, then the experiments take about a minute or two. So we did work out the kinks with the pulse simulator, and we contributed the notebook on Hamiltonian tomography to the Qiskit textbook. So if you look at the Qiskit textbook, chapter 6.7, you can follow along and see exactly what we did. And that's open to anyone because anyone has access to the pulse simulator. However, you need to be a premium member of, say, the IBM Q Hub at Institut Quantique in order to have pulse access on multi-qubit devices.
Yeah. All right. I don't know if there's any other questions in the. And we've pretty much reached our time, but maybe I can ask last one,
Sure.
Just about the Hamiltonian. So I understand that you simulated this Hamiltonian. I'm not just quite sure that this Hamiltonian really reproduced a braiding between fermion, like Mariana fermion. Maybe do you have an intuition to say why this specific Hamiltonian will do braiding?
So I think the thing is this is the simplest Hamiltonian that will be like a toy model of braiding. We do have John went through some painstaking math to extend this to a proper Majorana that consists of, a number of these segments, which is really what you would want for I would say like a non-toy model of braiding. And so you could extend this to multiple qubits, in the future, and maybe we could run a simulation on that. But as far as I know, this would achieve braiding. It would be more proper if you had more qubits, so that you could get less degeneracy breaking between the two parity modes. But I think it's all good.
Okay. Yeah. All right. So thanks again. Very nice talk. It was very, very interesting. Again,
thanks so much,
the full stack. So we'll be in touch.
Yes, absolutely.
Sure.
And thanks so much for having me, and I can't wait till I can visit in person.
All right, yeah. So okay, so thank you everybody. And yeah, I'm not used to these talks, so I think it's the end. So maybe see you next week.
Thanks for the questions, and I'll see you around.
All right, see you guys.
Goodbye.